if I can go back to it, is we looked at this example. There it goes. Where I gave us a graph of g of x, and g of x is an integral defined function. Remember, the big idea behind the second FTC is how we take the derivative of integral defined functions. But at the end of the day, when I have a function g of x, like I can do everything else I've always done with functions. Like I can find its zeros, I can find its intervals of increasing and decreasing, I can find the concavity, I can find tangent lines. Anything with a function, I can do with these integral defined functions, also called an accumulation function. Yesterday, we looked at how we could just evaluate these functions, which actually ended up relating to the net area under the curve. We saw that this g of x is really the integral from 1 to x of this function of f. And so if I was finding like g of 3, that literally meant the net area from 1 to 3. And then where the second FTC came into play, again, it doesn't always show up when you're doing these integral defined functions. The second FTC showed up when I had to find the first derivative of g, since I was taking the derivative of an integral. And then we saw how like g was representing the net area, as we said before. G prime ended up being the same thing as f, which would be finding the value on a graph. And then g double prime was the same thing as f prime, which is related to the slope. So where we're at today, I just have several slides of just like a lot of questions we looked at first semester, but in these contexts of the integral defined function. So like looking at this example, I went ahead and just left everything the same. We have the same g of x, and g of x is a function of f of t. Bear with me 1 second, guys. My pen is frozen, so I'm just going to X out one note and come back to it. But we're going to evaluate, cool, my one note is thinking. But we're going to evaluate g of x again, talking about its derivative and second derivative using that function of f. And we'll just awkwardly wait while it says my one note is cleaning up from the last time it was open. Cool. All right, guys, fun story. I said my Surface needed to restart, so I'm going to pull it up on my Dell and write with my fingers. So it's probably going to be super messy, but I'll be able to at least do something. And then once it comes back up, I'll switch back over. All right, so here's going to be my messy kind of finger writing while my Surface restarts. But looking at this, we are asked to find the zeros of g. So we want to interpret this as an integral defined function. So if I want to find the zeros of g, let's just kind of think about what that means algebraically. If I need to figure out where a function has zeros, we know that that's where it's going to cross the x-axis, or basically know that that was where we set the y, the actual graph, equal to 0 and solve. Well, in this case, g is an integral defined function, so I do want to find when g of x is equal to 0. And I know this handwriting is the worst, but g of x is equal to an integral. So instead of looking for where g is equal to 0, I am looking for where the actual integral itself would be equal to 0, since g is defined by this integral. So if I'm looking at where g is equal to 0, we're looking for the integral is equal to 0, realizing that this integral is at 1, so we want to find all the places where if we start at 1 and go over or forwards, backwards, or don't change, that net area is equal to 0. The first one is going to be the easiest one to find. We know that the integral from like 1 to 1 is 0. Like we don't go anywhere. We don't have any net area. So one place we're going to have a 0 on the graph is when x is equal to 1. Why is that? Again, because the integral from 1 to 1 is going to be equal to 0. The other case where this is going to happen at is we're going to have to actually use the integral and find the definite integral to figure out when all that area is going to cancel out. So again, we do want to remember that the area for this is starting at 1. So I'm just going to kind of work my way from left to right. And again, I just want to figure out when the net area is 0. Because when the net area is 0, that's when g of x itself will also be equal to 0. So in this first spot from 1 to 4, if I just kind of divide this up into shapes that I know, we see that this is going to have an area of 1, 2, 3, 4, 5, 6, 7, 8, I believe. 9, just kidding. It would have an area of 9. And so basically the 0 is going to be when we have a negative area of 9 that will cancel that out completely. So like if I'm looking as that continues, from 4 to 5 is -1. Then we have -1, 2, 3, 4, 5, 6. That first little region is -6. So once I hit -3 again, then we know that that net area is going to be 0. So that 0 is going to be right at 10. That is where the net area is going to be 0. So we have zeros on the graph in 2 locations at 1 and 10. I know there's not going to be any more locations. The rest of that graph as I continue through is negative, so there's no way that we're going to go back positive to negative again. I could move backwards, but if I'm starting at 1, there's not much region before 1 for me to cancel out an area and have a net area of 0. Questions on that problem? All right, so looking at the next one, and my surface is slowly coming up, so I'll be able to get off my finger in a second. Next thing we want to do is number 4. And again, anything that we did first semester can definitely show up again when we're looking at these. So looking at number 4, it tells me to find the absolute minimum value of g. So if we're looking for the absolute minimum value of g, think back to some things that we did first semester and ask yourself, well, what do I need to show in this class when we need to find an absolute minimum value? To do absolute minimums or maximum, I'm just going to type this up, it's a little bit easier. We know that we basically are going to need to do a candidates test. What goes on our candidates test? Remember, we have 2 things. We have to have the endpoints, and then we also will have places where the derivative is equal to 0, or where the derivative is undefined, which is not really going to happen too many places for these integral defined functions. And remember that when you do a candidates test, it is just a t-chart. So you're going to have 2 columns, one with the x's and then the other one with the y's. So I'm going to go ahead and create my candidates test. We have x and g of x. And then on our candidates test, again, are going to be your endpoints, and then also any place where the derivative is equal to 0. And that's where the second FTC is going to come into play. So if I'm looking at this region, I do see that it does have closed intervals based off of what I see on the graph. So I have the endpoints are going to be at 0, and then they're also going to be at 12. And then I do want to go ahead and find where the derivative is equal to 0. And so we want to find the absolute extrema of g. So I am going to want to find when g prime of x is equal to 0. We already talked about the relationship here. G of x is an integral defined function. We can use the common case. So g prime of x, we know is literally the same thing as f of x. So we're looking for where f of x is equal to 0. So if I'm kind of relating these 2 things together, g prime is equal to 0 when f of x is equal to 0. Well, where is f of x equal to 0 at? It's equal to 0 at 4, 8. Also at 0, but that is already on there because it's an endpoint. So I'm going to add to this t-chart where the derivative is equal to 0, which was at 4 and then 8. And then we want to go ahead and evaluate this. We do want to remember that when we're doing a candidates test, we are plugging this into the original function. And in this case, the original function is g of x. So we do need to remember that g of x itself is an integral. And so that first one, for example, if I want to find when x is 0, we're simply evaluating the integral. 1 is at the bottom, so 1 to 0 of f of t dt. And then we just want to evaluate that like what we did. And we already did that one. That was 1 to 0. We are moving backwards. So we would say that it has an integral of -1. What is g of 0? G of 0 is -1. And so then we want to continue that for the remaining integrals. I'm going to give you a chance to try those on your own, and then we'll check it. So like for the x equals 4, you're finding the integral from 0 to 4. From 8, you're finding the integral from 1 to 8. I said 0 to 4, I meant 1 to 4. And then for 12, we're finding the integral from 1 to 12 of f of t dt. And while you're trying that, my surface is finally back up again, so I am going to switch screens so I can teach like a normal person. And big idea here, as while I'm getting kind of this fixed back up, we have to remember that g is defined as an integral, and so when we're talking about g prime, we're looking at f. And again, when I'm working on these, all of these answers are coming from the net area. The answers you should have gotten, -1, 9, 3, and -4. Again, all these are being measured from x is equal to 1. So then your answer will be find the absolute minimum value. We will say that the absolute minimum is, you're looking for the lowest value. So the absolute minimum is -4. It is located at, and now it sinks so you can't read any of that, is located at x is equal to 12. All right, and there's third period's version that will be a little bit easier to read. That was a mess, but any questions on that problem? Cool, let's hope the rest of class goes a little bit more smoothly. So continuing that, again, anything that we did first semester can definitely show up again when we're looking at these problems. The next ones I want to get is when we're talking about intervals of increasing and decreasing. So again, this is going to combine knowledge that we did from first semester with this idea of the second derivative test. We are going to talk about justifying your answers. Again, justifying your answers for these problems have to be clear and concise. You also have to always make sure you refer to the given graph. And I'm going to make a note about that. All your justifications will always have to refer to the given graph, which in this case, the given graph would be the graph of f, but we're going to be talking about g. So we'll have to be careful with how we kind of do our justifications. If you remember from first semester, I like writing out my justifications first and then finding the intervals. So for number 5, it says on what intervals is G increasing? Well, we know that G would be increasing if G prime of X was greater than 0. But I don't have the graph of G prime, but I do know what G is. Using the second FTC in the common case, I know that G prime of X is equivalent to f of X. This is a statement I can use because f of X is the graph that is given. So when I say because G prime is greater than 0, I left a space there because I'm going to write it as G prime of X, which is equal to f of X, which is greater than 0. So where would G be increasing? G is increasing wherever f is greater than 0. Well, we're looking at the graph of f. Where is f greater than 0? F is greater than 0 on the interval from 0 to 4. Talking about things that you must include, you have to mention, of course, G prime is greater than 0. Like that is what's making a function G increase. You also, though, have to be very clear and state clearly f of X in there because that is the graph that's given. And you have to clearly state that f of X is equal to G prime. That's not a long statement, but there are kind of like multiple things going on there that you have to make sure you state to receive all credit for that question. Questions on that one? All right, so let's go ahead and look at the second one. The second one is talking about on what intervals is G concave up. So again, I often like starting with my justification first. We know concave up, we often think of that as the second derivative. So we might start it off by saying because G double prime of X is greater than 0, that's when something would be concave up. We know that if G is the integral and G prime is f of X, then I know that G double prime of X would be f prime of X. So we know that it would be concave up when G double prime of X, which is equal to f prime of X, is greater than 0. But there's something wrong with that statement. The graph we have is of f, so I can't really use f prime to justify my answer. So I do want to think of an equivalent statement I can say. So I did do that just to kind of show you what the wrong one would be. But an equivalent would be, we know there's another way to talk about concavity. We know that concavity would also be true if G prime of X was increasing. Think back to that table we did all the way back in Unit 2. G prime of X is equal to f of X. Well, where is G prime of X equal to f of X increasing? Wherever f is increasing. And f is increasing from 0 to 2, and then also from 7 to 8. And again, your answer must include the given graph and then the relationship that we have to G, the one that we're talking about. Questions on that slide? All right, just a few more. Looking at the next problem, again, this is a lot of stuff that we did first semester, just kind of putting a little bit of a different spin on it. 7 and 8, at what x coordinate within the interval, and I chose an open one, from 0 to 12, does G have a horizontal tangent line? Again, think back to first semester. What would it mean for G to have a horizontal line? Well, that would mean that G prime of X is equal to 0. Using the second FTC, we already said that G prime is equal to f of X. So I want to clearly state that in my answer. G prime is equal to f of X, which is equal to 0. Well, where is G prime equal to 0? Where f is equal to 0, which does occur at 3 places, but we do have an open interval, so we're not going to include 0. So that's going to happen at 0 and 8. And then I have a follow-up question for that. Looking at question 8, it says that each of those x coordinates we found state whether G has a relative minimum, a relative maximum, or neither. I'm going to answer these in the space kind of next to it, just so we can kind of see everything.
Mr. Ben?
Yes, Ben?
Wait, why do you not include 4 in it?
I don't know. I wrote it wrong.
Wait, so you don't include 0?
Not including 0, but I am including 4. Sorry, I said it backwards. and wrote it backwards.
So you don't include 0 because it's not like a
Yeah,
less
not
equal
included.
to.
Yeah, is not equal to, but I should have put the 4 there because it is included.
Okay, I get it.
Thank you. So now we want to determine whether we have a relative minimum, maximum, or neither. Think back to first semester, we do have like the first derivative test and the second derivative test. I'm going to be honest with you, the first derivative one is going to be easier. Remember, when we're using the first derivative test, we are looking at sign changes of the derivative. So if I'm talking about extrema on G, I am basically looking for where G prime changes signs. We know that G prime is the same thing as F. So if I'm looking at 4, I see that F goes from positive to negative. Well, if F goes from positive to negative, then G prime is going from positive to negative. So I know that x equals 4 would be a relative maximum. How do I know that? I want to clearly state that G prime is the same thing as f of x, and then how I know it's a maximum, because it changes from positive to negative. Same thing for x is equal to 8. I can see that x equals to 8 is going to be neither of those, because G prime, which is the same thing as f of x, it stays from negative to negative. So I'm going to simply state that as doesn't change signs. We also I had the interval there to kind of go back to what Ben asked, one, correcting my mistake. I didn't leave 0 on this open interval because you would only be asked about 0 if it was like an absolute minimum or an absolute maximum, because it's on an endpoint. In calculus A, B, and BC, we only refer to relative extrema when they're within an interval. So the way I worded that question would be kind of what the AP exam would do as well, only classifying points within the interval as being a relative min or a relative max. Any other questions on that one? All right, last one. This one, in all honesty, is not the most important one, but I did want to go ahead and kind of make some connections between an integral defined function and what the graph of G would actually look like. So again, to be perfectly clear, you're often not going to be asked to graph G. But you do need to be able to kind of make a connection in your head, like, well, when I see G, it really is like accumulating area in this case. So these are all the answers we had found previously. I went ahead and typed them up beforehand, and I'm just going to plot all the points we found when we answered numbers 1 through 8, and then we'll kind of see the relationship and why I call this an accumulation function. So like in number 1, we just evaluated G. This is what we did yesterday. We found that G of 3 was 7. We found that G of 1 was 0, and G of 0 was -1. Number 2, we saw that G of 6 was 6. We did that one yesterday. Today we picked up on the zeros of G, and we saw that the zeros of G were at 1 and 10. That was when the net area was 0. We also did a candidates test, and some ones that we didn't have on there was the absolute maximum. Didn't ask for it, but it was when x was equal to 4. And then the absolute minimum was when x was equal to 12. So I'm going to highlight what G looks like in pink. It's concave up from 0 to 2. And 7 to 8. So it looks something like that. So the connections I want you to make, again, those just came from the answers we found. Why I call this accumulation functions, you have to imagine that pink is like the value of the net area. So like as I move across this graph, we can see that we have like starting at 1, moving backwards, so that would be a bunch of negative area because we've moved backwards along that curve. But moving forward, since we're starting at 1, we're like adding area, adding area, adding area, and we keep on adding area up until 4. So that's why the maximum was at 4. And then once we pass that 4, we're like, subtract to area, subtract, subtract, and then you just keep subtracting the area. It never goes positive again, so we just keep subtracting the area. At 10, we saw the net area was 0, but then we just kept subtracting area till we ended up with this minimum value at x is equal to 12. So you can kind of see how that pink graph is related to the graph of f of t, and why I'm going to refer to g as an accumulation function, because it's accumulating area, and eventually we're going to expand this to like accumulate all sorts of things, like people standing in line, to maybe like rainfall, to population of an animal, like anything that grows or shrinks, we're going to be able to model with an integral function. So despite those technical difficulties, that's all the notes I have for today. So I don't have as much time as I planned for you to work on your own, so I do apologize for that. But your assignment that you're working on, so you're going to continue working on homeworks 1, 2, and 3. At this point, you can do now all of homework number 3. Homework is going to be due on Thursday. That is the day of your quiz. Tomorrow is just going to be a review and practice day. So you will have I'll have a brief meeting to take questions and talk about the quiz. But for the most part, tomorrow will be a day for you to work on homework and ask questions. And then your first quiz of the semester is going to be on Thursday. So with that being said, if you're good to go, then you're more than welcome to go ahead and sign out of this meeting. If you want to stay back and ask any questions, definitely do that as well. Class ends at 1:10, so I have about 13 minutes if you did have any individual questions you wanted to ask. If you don't have any questions, then I will see you tomorrow.
Can you go to graph 4 for a sec?
Yes.
Thank you.
Let me go to the one that's cleaned up from third period that I didn't have to use my finger on. There's the nice looking one.
Thank you.
You're welcome.
Have a great day, Mr. Brown.
See ya.
Mr. Brown.
Yes, Seth. See you, Dave.
So on homework 3.
Mm-hmm.
So for to find the equation of a tangent line, I know you have to find the derivative of the function. The derivative of that function is just secant of x, tangent of x.
Mm-hmm. So you would know f prime of x, secant of x, tangent of x. And so the slope would be at f prime of pi over 4, right?
Yes.
You also need to have the point, and the point would be using the original function. Well, the original function would be an integral. So you would just evaluate that basically using the first FTC, like first semester stuff.
Okay. And then for the finding the horizontal tangent line, I was
so we know horizontal tangent lines would be when the derivative is equal to 0.
right.
So use the second FTC to find the first derivative,
which is x squared.
And then just set that equal to 0. And solve.
Okay.
It can be more complicated if you have of course the general case, but same thing, you want to find the first derivative and set it equal to 0 and solve.
So for when you have the common case, from the number 7,
Mm-hmm.
is one of your zeros always going to be the same, like 1 or the same number? Because that would cancel out the net area.
Are you asking when the derivative is equal to 0 or the zeros of the original function?
Like the zeros of the original function.
The zeros of the original function, you will pretty much always have whatever number the constant is, because that will always be 0.
Okay.
Like it's defined like in calculus, like it's technically a property. I don't really teach it because it's kind of known, but like if you go from a to a of an integral, that's always going to be 0.
Okay, yeah, that makes sense. Okay, thank you.
You're welcome.
Have a good day.
See ya.
Hi, Mr. Brown, I just wanted to ask about like your formatting in OneNote, because like
Uh-huh.
at the top you have like that purple bar with all your markers,
Mm-hmm.
and I was just wondering how you got that, because I'd like to be able to like change around what pen I have faster,
Yeah.
and I just
So
can't figure it out with the
I
settings.
remember how I did it. I click on this little option right here. It's like a little ribbon display option.
Yeah.
And then I clicked on to always. Which one is it? Did I click on? Because we're usually on auto hide, and it's the on do the show tabs one is what I do. And then to customize this, it's like the little drop down option. And then I just do more commands just so I can get all of them. And if it loads, oh, don't tell me my surface froze again. There it goes. You can choose what you want. So like I have these on my surface. The one I have at school, I also include like the forward and back option just when I'm using my smartboard. But you can choose whichever commands you use the most often. The only thing I hate about it, that's obnoxious, so you can only choose like your favorite pins, and it will let you do all the way up to like 8, depending on how much will fit up here. But there's no easy way, and I'm sure you know this, to like the favorite pins are the ones that show up here. And the only easy way, like I wish my thicker ones were up there, but you have to like literally one at a time, like right click and do move up, and I just don't have time to do all that. I mean, I guess I could, but I'm too lazy to do all that. So basically, like whatever your top pins are will always show up, and I choose like a few pins and a highlighter. I think you can also make the eraser show up there, but it's basically the show ribbon, and then you can edit the options from there.
All right, I kind of worked my way up to that, but whenever I click the full screen thing to like put away the column, it goes away on my end. I was wondering if you'd like.
Try after you move into full screen, click on show tabs. I think the first one I did might have reset when I moved from the not full to full screen.
I fixed it.
Okay, yeah, I don't know. OneNote could be designed better, but yeah, there you go.
All right, thank you.
You're welcome.
All right, have a good day.
See ya.